So, welcome everybody. Thank you for coming. Another meeting of our online half a reading group, half a research seminar. And today we're happy and proud to have with us Stefanos Leonardos from King's College, one of the organizing team and the initiators of this seminar. And he's going to tell us about Q-Replicator dynamics. Stefanos, the stage is yours.
Thank you, Kelly. Thank you for the introduction, of course, for having me. And also thank everyone for attending the reading group. So today I will try to speak about Q-Replicator and other dynamics. It's a bit misleading to the title of my talk that I will only speak about the Q-Replicator. So let's start. So my presentation, I will try to talk about three different things. So the first part is a bit unrelated. So I will start from experience weighted attraction learning, and we'll try to derive the replicator dynamics as the continuous time limit of this learning rule, which is very general. Then I will connect this to Q-Replicator. Of course, the connection, it's a bit loose. There are very different ways to derive the Q-Replicator. I will not go into those details. And then in the third part, which is a bit more research oriented, I will talk about the performance of Q-Replicator and how to compare it. So given that we have a broad audience with different backgrounds, I hope there is something for everyone here. So the first part is technical. It's like a whiteboard session. I will do some calculation. The second part is just some definition. And the third part, as I said, is maybe a bit more research focused, but it's also not very complicated. So maybe everyone can follow, even if they are not interested in that research. Okay, let's start with the first part, experience-weighted attraction learning. This is a very general rule that was defined, introduced by Cameron and Co. I give some references at the end of this part. So yeah, for now, we can have a look at this, and in the end, I will talk about the references. So where was this developed and some main citations in the field. So here, let's go directly into the rule. I think you can see also my pointer, right? The highlight. Yeah, okay, all right, okay, great. So let's go directly into the learning rule. So, and also, by the way, feel free to interrupt me with questions or send in the chat if you have any objections or any questions. Yeah, just feel free to interrupt me. So let's go directly into the learning rule. The probability for a player mu to select an action I at time t is given by this softmax. So here we have one parameter, which is beta, and this is defined as the intensity of choice. I will go into what are the Qs right afterwards, but first the beta. It means to choose if beta is equal to 0. You see that simply all these Qs cancel out. So in this case, we choose all actions with equal probability. This means that we essentially ignore the signals that the player ignores the signals that they have from the environment. And if this beta is equal to infinity, or actually tends towards infinity, it's very large, then the player simply chooses the action with the highest Q value or signal. So what are these Q values? These are called the attractions, and they are updated according to a fairly complicated rule. A rule that has quite a few parameters, and we're going to look at these parameters right away. So just to recap, very simply how experience-weighted attraction learning works, EWA learning. The players update some attractions, some scores, and then they use the softmax over those scores, using also the parameter beta, which is the intensity of the choice. So far, so good. So let's go to see exactly, let's go into more detail about the experience-weighted attraction learning, and what are all these parameters, and whether we're going to simplify any of them. So this is a very general family of rules that captures many different learning paradigms. So reinforcement learning, average reinforcement learning, and some very different learning models. And even in the literature, this update rule appears with some variations. So some have also an additional parameter here that depends on this number. But now let's focus on this one. So the general idea here is the following: that the attractions are updated as follows. So the new attraction in the new point in time for action I for player mu is equal some discount of the previous attraction. So it is we have a scaling factor. So here gamma is less than 1. So this is this captures essentially the memory of the player. And if, for example, this is equal to 1, this means they forget completely what has happened in the past and only focus on the current world. If it's equal to 0, this means that they have complete memory, so no memory loss at all. Now here, the first parameter that we're going to look at is delta, and we're going to get rid of delta in what follows. So delta is simply a relative weight given to updates of attractions of actions that are played versus those that are not played. So here we have the indicator function, and the indicator function is whether the action that player mu took at time t, so the strategy or action, is equal to the action I that we are currently updating. So for example, if delta is equal 1, you see that this here disappears, right? And we have an update for every action, so regardless. If delta is equal to 0, then we update only actions that are actually used. So this is 0, and this here is 1, so it remains, so it's equal to 1 only when we are looking at action I, which is actually used at this point in time. All right, so it's called bandit learning and has different names. The next parameter that we're going to look at here is this calligraphic n of t, which is a weight factor of recent rewards. So this can be, for instance, the number of times that we have played the game, or this can be a constant after some time. It can have very different values. And the reason now, the model that we're going to look here, there are many special cases of interest of this dynamics, depending on what delta, on what calligraphic n you choose here, or whether you put an additional factor, depending on the calligraphic n here, and the choice of gamma, etc. But here we're going to look for a delta equals to 1. So we're going to look at the model that updates all actions, not padding learning. So we're going to update all i's, and we're going to motivate it through this image that I have there. And the calligraphic again, we're going to assume that it is constant. This is motivated in the literature in the sense that we have reached the steady state, so we don't really update anymore the number of times that we have played the game. Now, generally, how we think of this model, I mean, the calligraphic n that it's constant is not really important, as you see in the next step. What is important here is why do we choose delta equals to 1? So why do we choose to update all the Q values, all the attractions in every time step? And the time scales that we have here in mind are the following. So the bottom time scale, the interaction, is when the agent interacts with the environment. So chooses the actions and plays, receives some reward and sees what happened in the environment. The adaptation is when they change their distribution. So the X that we saw, the softmax that we saw in the previous slide, and the top time scale is the environment. So maybe one example that has proven useful sometimes here is to think of trading in a financial market, right? Or although these models are not necessarily motivated by financial models, you can think, for example, that a trader who has several strategies, consider several strategies, deploys them every day and all of them during the day. Let's say they have 10 strategies, and one of them, let's say they play with a very small probability, so 1%. During the day, they are going to observe what happened with this action. So because they are going to, let's say, interact with the market 1,000 or 10,000 times. Then they have the adaptation. So every day or every week or every month, they choose to change the strategy. And then they have the economic environment, which changes more slowly the macroeconomic environment. Maybe this model can help us think about the timescales here. So this is the motivation that we are not going to only have this bandit learning, where we choose one action, observe that reward, and do a full update, but we have many rewards and many interactions with the environment, and we are going to update all the attractions. All right, so for data equals 1, we motivated that. We said now that we have these time scales in mind. So an agent who plays all their actions and gains information about all of them. This calligraphic n is constant. I mean, as you see, right. So we can have different models where this changes, but it simply it can mean, for example, that we stop learning, right? So after some point, we want to increase that, they keep increasing, so we don't really care about the current reward. In this case, we care, right, about the signals that we're receiving. And now the previous rule gets this form, right? So the new, I also eliminated here the dependence on player mu because we are looking on just one player. And I also eliminated from the reward the dependence on the strategies of the other players. But that's the notation, right? These rewards depend on time t. And on time t, for example, in the financial market, which is a multiplayer game, you can either model the other players or say they are part of the environment. So, and I just have a variable reward. So I play the same action, but the reward that I receive is different. Now let's get rid of this constant n star. I simply multiplied throughout the equation. And as you see, the only place where this appears is next to our Q values, right? So I can simply rename the Q values and call them Q tilde. And then I have exactly the same equation, and I got rid of this constant. Many people choose to select this constant equal to gamma, for example, and have a convex combination of the reward. You can have nothing here, or you can have a constant different from gamma, or you can have a variable parameter. But in any case, you can simply look at this equation because having a constant calligraphic n amounts to rescaling the QIs, or equivalently, rescaling just the beta, because as you remember from our softmax, the QIs only appear together with beta. So having a rescale QI means that I have a different parameter beta, and since we are looking at any positive beta here, it doesn't really matter, right? So now this equation, only with some reservation, I call it Q-learning, because Q-learning has many different names and many different forms, and especially when we're looking in Markov settings, we also expect here a state transition and the classic Sutton-Barto definition. But I also provide a reference where the derivation that we're going to do now from this rule to replicator dynamics also applies to that case. So if you're familiar with some slightly different version of Q-learning, it also applies here. It doesn't really matter. All right. So another thing that we mentioned now, we're going to be interested, I still don't have it on the slide, but it's going to follow next. We're going to be interested about the continuous time limit of this dynamic. Now, of this update rule, right? Now, this is in a discrete time. So we have time t on the right-hand side and time t plus 1 on the left-hand side. But now we're going to be interested to derive a continuous time limit. All right, so a first thing to observe here is that these rewards, as we said, are stochastic, right? So this is a stochastic system because the rewards depend also on the actions of the other players, and they change, or in the of the environment, and they change in a way that we cannot. It's not deterministic, right? We cannot control. So when we have, when we let's say deploy our action number 1 during a day 1,000 times. And we want at the end of the day to update our attraction and update our policy on next day through the softmax that we saw here through this rule. The natural thing to do is to take the average reward, right? The average over all this action. And then we have a deterministic system, which essentially says take the average reward of this of all the times that you selected action I. And under the assumption, of course, that the environment and the actions of the other players change more slowly than the interactions that take place with the environment. Okay, let's try to derive. I don't know if there are any questions or any objections up to now. All right, if something comes to mind, feel free to jump in. So now we're going to derive the continuous time, going continuous time. All right, so how do we do this? We start from this equation. I simply did some small rearranging here. So I had this 1 times qi. I brought it on the left-hand side because I want to make the definition of the derivative appear later. And now I take here this t plus 1 and I make it t plus dt, right? So we make the time interval smaller. And because we only care about the reward in this time interval, we can also multiply the right-hand side with dt. In the next step, we simply divide both sides with dt, and then we take the limit. This cancels out on the right-hand side. And on the left-hand side, what happens is we have the definition of the derivative, of the time derivative, as you see here, with dt going to 0. And on the right-hand side, we don't have any dt, so it's exactly what we have before. And that's the time derivative of the q values. So it's just a technical step, right? So I don't know if there is much intuition here, or any assumption that goes into play. There are different ways, more technical and maybe more rigorous. Maybe if you are bothered with the multiplication of the dt on the right-hand side here, there are even more detailed derivations in the reference that I will provide. But essentially, that's just the technical step. What we really care about is to have an expression to take the continuous time limit of the softmax equation, so this one, and see how the how the probabilities of its action are updated in continuous time. So to find the continuous time limit of this, it's just the last whiteboard part of the presentation. So just show a bit of patience. So I take here the time derivative of the probability, and this is of course the time derivative of this expression, right? The softmax. And after some very standard analysis that I haven't included here, so really taking the derivative of exponential functions, what we end up with is this equation. So we have the constant beta, we have the same probability xi on the right-hand side, and then we have this time derivative of the attractions that we calculated before. Here is a dot that shouldn't be here, is a typo. And we have this difference, which already reminds us of our familiar replicator. So we have something, and it's relative difference from the expected value of this one quantity, right? Here is the time derivative. But we want to get rid of these q values of this attraction. And so how do we do it? We use what we calculated before, so that the time derivative of this price is equal to the current reward minus gamma, the previous attraction, the current attraction, and that by solving this softmax equation, exactly this one here that we had before, so the definition for qi, we just find that it is equal 1 over beta times ln of xi, plus some constant that depends on the whole distribution of the xi, and it's the same for every I. That's why I write it. So we can, using these two expressions here, essentially we can substitute the qi, the time derivative of the attractions, with the current reward and the xi. And this z that will disappear because the z will show up here, and it will show up here, but it's constant, and this whole sum come up to 1, right? So these are probability weights, so it will cancel out and disappear. So without a lot of complicated algebra, we end up with this equation where I also divide it with xi so that we have a more clean expression on the right-hand side. So what do we have here? We have this beta parameter times this relative difference of the reward of action I and the average reward. Oops, sorry. Minus gamma. Gamma was another parameter here, was the memory loss. And times now this ln term. I will go into more detail into what these terms mean in the next slide. But for now, just to clean up a bit this expression, to have all, let's say, our parameters at one place, I will divide the whole expression by beta. And since beta is a constant, right? So, or let's say take a common factor on the right-hand side, take the beta as a common factor. Now this is a constant, and this is the rate of change of the dynamic. So it simply means faster time or slower time. So we just need a rescaling of time to get rid of beta. And here we have gamma over beta in just one parameter that we will call capital T. So the dynamics, after all these calculations and after removing all the dependence, all the terms depend on T. So I simply remove the dependence on T of all the terms in the box expression. And that's the continuous time derivative of the dynamics. Let me write it here on the next slide. It's exactly this box expression now, but I have write it in a more clean way. All right, so that's a derivation. I don't know if you have any question of this technical part. Otherwise, we can start discussing this dynamics. Okay, now, I mean, I have given a name here, smooth Q learning, because it's, let's say, smooth in time. So we started from a discrete time to something continuous time. It appears with different name, and really let's not give a name to that dynamic. So I think there is not a uniform name about this dynamic. Also, there is a lot of fun about how you call T. So depending on your background, because these dynamics are quite ubiquitous in the learning literature. So if you are a physicist, they are called temperature. If you are an economist, you can call it degree of rationality, because if you remember, this was how you select actions based on the attraction. So if you are perfectly rational, you should just select the best action. If you are irrational, you select all actions are random. If you are a computer scientist, this is typical regularization parameter. And now, because there are many people, so let's say here, if you're computer science with, I don't know, background in math and or game theory, who came into CS through different routes, you can also call it expression rate. So, I mean, I don't take this as a taxonomy, right? There are many different names on this parameter, and many different disciplines that are looking at this dynamic.
Can I ask one?
Yes.
So what happens in the case there is more than one optimal action? I mean, when beta is very large, I understand that you choose the largest, but then it suggests that you choose them with equal probability. There is no way differentiating between, because that is not an equilibrium behavior in general. I mean, I'm not sure whether you ever wind up at mixed actions. It's probably only referring to the dynamics, but in the end, uniform distributions are not normally anything like equilibrium.
Correct. That's correct. So there's these dynamics do not necessarily find the equilibria, but this is yeah, they would go to that. They would go to the uniform distribution between the best action if you have a complete tie, but also there is no general guarantee that they converge in all settings to the equilibrium. So, thanks for the comment. All right, so these dynamics, what they do, they have these two terms called also exploitation and exploration. And the reason that they are called exploration is because we have this ln of x here. And this is, as you see, the term, the whole right term does not depend on the actions of other players, right, at all. It only depends on the current distribution. And it's, let's say, the self-information or the degree of surprise is an idiosyncratic term. and let's say the smaller the xi here, right? If it's close to 0, you will get a value close to minus infinity, if I'm not wrong. So with a minus in front, it will make your dynamics explode in that direction. So you get a lot of information. And this pushes your dynamics to increase in that action, right? So the way that you put in that probability to increase, that's because you have this term here. We discussed these terms, and here you have the other terms that you have. Here you have the individual reward of action I, the average reward, and here the average self-information or entropy, right? This is also called entropy. So it's tempting to understand a little bit more these dynamics. We can rewrite them in the following way. So we have the, as you see, what we have here is exactly one term that we can call our new reward. So our reward is essentially Ri minus TL and Xi. So we can give it a Ri tilde name, doesn't matter. And here we have the average of these terms, right? So if we group them simply in a different way, and essentially, if we write them in this way, what we have is replicator dynamics in a different space. We have the replicator dynamics in the original space, of course, if capital T is equal to 0. And we have the replicator dynamics in a space of modified reward, where this ln shows up of the current probability, if we group it that way and we have a different thing. So in any case, the main learning approach or paradigm of this dynamic is what we have in mind from the replicator dynamic. So the performance of action I in comparison to some average performance of the other. Does it make sense? All right. All right. Okay. So, I mean, there are very, very different ways to derive the replicator dynamics or to justify them. It's just only one way. And this is here I provide some references of the first part. This is the end of the first part. Many papers that have looked at those. I think it's a chronological order, the way that I present the papers here. So very briefly, let me go through this literature. The first papers are from Kammerer and Ho, who introduced the experience-weighted abstraction learning. And then it has been used quite a lot in physics, in game theory, it started appearing in computer science conferences. And of course, it's not exhaustive, the list. So if you have worked on this dynamic and you don't see your name here, know that many people have derived them and have used them in the research. The papers that I use mostly here are for this presentation work from Sato in Cratfield, from where I have also had this figure, and the Gala and Farmer paper in PNAS, complex dynamics in very complicated games. And there are also, for the economists here in the group, interesting work currently in this dynamics. For example, paper 12 here, towards the taxonomy of learning dynamics in 2x2 games and games in economic behavior. So the state of the art of classifying and understanding these dynamics in full generality are still small games. So there is a lot of open work to do here. And just as a notable paper that I haven't had highlighted here is number 4, which has exactly the Q learning from Sutton and Bartle and derives the replicator dynamics from that model and also for state-based interaction. So not only for repeated games as we have it here in mind, but also with state transitions. All right, that's part 1. I don't know if you have any questions or anything that you'd like to discuss about it.
Stefanos?
Yes.
Maybe just a short question. When you introduced, experience-weighted attraction with this flexible delta parameter, I see how delta parameterizes, if it's 0 or 1, how it parameterizes bandit learning versus full information. I don't know what that's usually called, updates. Is there any Are there any benefits in looking at interior deltas? Do people, is there like an advantage if I choose delta equal 1/2 and weight stuff that I actually chose higher than other things? Is there like...
Yeah, that's a good point. That's a good point. Let me see. Maybe there is let me see. The given interpretations here for intermediate values of delta. Yeah, interesting. I don't know what that would capture exactly. An intermediate value of delta.
Yeah, I guess it would introduce kind of, I mean, if you're able to do delta equals, what was it? Delta equals 0. If you're able to do delta equal 1, then choosing delta less than 1 kind of gives you more dependence on what you actually chose, which should probably just be bad for you, introducing more variance and stuff. But I was just wondering if somebody actually does that.
Yeah, that's a good point. I haven't seen it, but I mean, there are definitely discussions on how to use it. But yeah, I haven't focused on seen in application the delta, intermediate delta. But there are theoretical discussions. I think especially in the taxonomy paper, which discusses all the values. So paper number 12.
Okay.
I think they discussed it there. But that's a good point. Yeah.
Thanks.
Thanks, Clement, for the question. Any other questions? All right. Okay, let's continue then with the arguably now a bit abrupt introduction, abrupt way to go to the Q-Replicator dynamic. But let's see it nevertheless. So the updates in the equation in the replicator dynamic that we just discussed depend on two quantities, right? So we have the left-hand side is the rate of change, and now on the right-hand side we have two quantities. The first one is the relative performance of action I, given the rewards that we're looking at, Ri, the original game, R tilde, a different game. But there is this notion that if the reward of action I is better than the average reward, then this should increase the weight of, create a positive effect for action I. If it's less than the average, negative effect, and if it's equal, it should be a fixed point. And the other quantity that we see on the right-hand side is the current probability or the current weight of action I. And I don't know if this is exactly something that we want to have exactly as it is there, right? So because if let's say this xi is very small, so if you play some action with very small probability, very, very small probability, it will make any updates on that action very slow. Or even if it's very large, again, it will affect the speed of the update. So in any case, the appearance of the xi on the right-hand side as it is makes very different update, affects the magnitude of the update depending on whether we are at the center of the simplex or at the boundary of the simplex, right? So whether we have a big xi or a small xi. While the first term was okay, right? The average term was okay. This xi, maybe we can control it. And that's one way to motivate here the Q-Replicator dynamics. Of course, there are other ways. I will talk about them in the next slide. So to control, let's say, the speed, we can rewrite the dynamics as follows. So let's simply first introduce the sum here, the denominator of xk. This doesn't matter because it's equal to 1, right? So it's we did nothing, and now we simply rewrite it like this. So I just wanted to showcase that this remains a weight, right? If you just focus on xk divided by the sum, this is just a number less than 1. It's just a weight. So you continue putting a weight on the rewards. That's it. And now the way that we can control the speed is by raising all the probabilities to the power q, where q is a positive parameter, no negative parameter. It can be 0 or positive. So now we have this xi to the power q, and here what we have, I lost my pointer, probably. What we have here is just, if you take this, it's just a weight of the reward. So it's a weighted average, right? That's all I'm saying. We have a different weighted average of the reward. And now what happened, so now this term is again the performance of Ri compared to a different weighted average of a different expectation over the reward. So because these are weights that sum up to 1. But now here we have controlled the speed. So let's say this q is very close to 0, right? So you take this can increase the speed towards close to the boundary, or it can make the boundary even stickier, even slower. So let's say if you raise the xi, which is the probability, is a number between 0 and 1, to a very large number. So if you, let's say, 2, 3, or 10, or whatever, then this becomes almost 0. So this means you make the dynamic super slow, close to the boundary. And for example, let's say going back to our financial markets example, maybe you want to introduce a new strategy, but you want to be very, very conservative of that strategy. You play it with a small probability. And even if it performs very, very good, you don't want to update to increase the weight of that trading strategy easily. So you want to be very sticky. Or vice versa, you are very risky, and if you introduce actions with small probabilities, you play them with small probabilities, but either perform good, you would be happy to quickly update their weight, and so you select here a small q. All right. So there are many important cases for this dynamic. For example, for q equals 1, right, we recover our standard replicator dynamics. For q equals 0, we completely, it's an edge case, we completely lose the dependence on xi on the right-hand side. And we have what we call smooth gradient descent, or because we have also protected gradient descent. For q equals 2, we have another notable instance called log barrier dynamics. I don't have it in the slide. But the whole, so that's only part 2, because I don't go into the details of how to derive it. I saw a question in the chat. Let me discuss it. Possibly the first derivation of the continuous time version of PWA and its relation to the replicator dynamics is by adopting two competing models of how people learn in games in econometrica. All right. Thanks a lot for many thanks for this addition and for liking this reference. Yeah. Thanks, thanks Ed for pointing to this paper. Yeah, as I said, probably in the audience we have experts who know this way better than I do. Right. So yeah, another expert that we have here in the audience and has a very nice, very interesting papers about Q-Replicator, Panagiotis, who formalizes this discussion about making the boundary sticky or less sticky, connecting this to how we measure distances inside the simplex, and offers a much more rigorous derivation of the Q-Replicator dynamics based on the Saxafani distance and adding a lot of geometric intuition to the topic. So here, the references that I used for part 2 are mainly, I forgot to highlight them, the Riemannian game dynamics and the learning in games via reinforcement and generalization. And yeah, the only other papers where I have seen the Q-Replicator dynamics in relation to game theory are also cited in this work. So that's essentially the only line of work that I'm aware of. Any comments or thoughts about this one? Part 2 was a bit short, but part 3 will also be about the Q-Replicator dynamics. that paper in the slide. All right, okay. Then let's proceed to part 3, and let's, which maybe is a bit less theoretical and maybe a bit more fun, because probably everyone is also a bit tired by now. So the question now is how to measure performance of game dynamics. So what does it mean to measure performance? So let's focus on some games that that we like and we understand. So potential games, which model interactions where coordination is desirable. Example, let's look at the stack hunt. Here, Yosif, my co-author, has done in his slides some very nice symbols for the animals. So here, players have two strategies. The one is they want to coordinate, right? They want to end up on the diagonal. If they end up on the top left, they get 1. If they end up at the bottom right, they get alpha, where alpha is supposed to be larger than 1. And beta is a parameter that captures the riskiness of the payoff dominant outcome. It's, of course, also an equilibrium, which is the alpha-alpha. Let's go to see a specific instance of the game where beta is 0. So let's see the game that I have here where I'm pointing. It's a very simple coordination game, let's say, in terms of presenting it, but it's not simple at all in terms of solving it, because it exhibits essentially all the complications that we want to study in multi-agent games. And I'm going to clarify what I mean. It has it presents, of course, the equilibrium selection problem. So we have here two Nash equilibria, and they have very different payoffs. So the one on the top right has a payoff of 1, 1, so a social welfare of 2, and one on the bottom left, where the rabbit is played with 0 probability, has a payoff of 2. So here you get the deer or the star. And here what Yosif has plotted and I have borrowed is the phase plot of the replicator dynamic. So you see that all these arrows here point to this equilibrium. All these arrows here point to the other equilibrium. So these are starting points, and these are the trajectories. And there is a very thin slide, very thin slide here that points to the maybe just one trajectory, even not at all, but we will see what happens here, that points to the mixed equilibrium, right? I think that we all know here that there is a third mixed Nash equilibrium, so I will not spend much time on it. All right, is it clear before we go to the next slide? Right, so how to measure performance? Non-coordination of pairs implies sometimes a gap in optimality, known as the price of anarchy. So that's a very common measure of performance in games. And the price of anarchy simply says, take the maximum social welfare and divide it by the minimum social welfare at a Nash equilibrium. This is larger or equal than 1, right, by definition. And in the price of anarchy is a worst case metric. So, for example, the price of anarchy in the game that we saw before, let's go on the previous slide. So the best possible outcome in this game has a payoff of 4. So it's this one here. It so happens that it's a Nash equilibrium. It could be anything, but it has a payoff of 4. And the worst Nash equilibrium, let's focus on pure Nash equilibria here, is 1. So it's 2, sorry, the total welfare. So it's 4/2, it's 2. In general, if we look at the parametric, sorry, I'm going back again. If we look at the parametric version of the game with 1 and alpha here, the best outcome has 2 alpha total welfare. The worst Nash equilibrium pure has a total welfare of 2. So the price of anarchy is equal to alpha/2 is equal alpha, and this goes to infinity as alpha goes to infinity. So we have a very simple representation of a game. So 2 strategies, 2 players. Very easy to represent and understand what happens, but it has all the complexities. It's super complex in terms of performance. So we have equilibrium selection problem, and not only that, the equilibria can be super different, right? So we can have as bad price of anarchy as possible. So the price of anarchy can be even equal to infinity. But of course, this is a worst case metric, and we don't really, when we look at the phase plot that we saw here, we don't really agree that things are so terrible in this case, right? Because we see that when we look at the dynamics, we see that many of them go to the 2-2 equilibrium. And this is not even the case where this is 10-10 or 20-20 or whatever, where the price of energy goes to infinity. We can imagine that even more and more trajectories will go to this equilibrium. So this motivates here in learning in dynamic environments. What matters is not exactly the price of anarchy, which is a static measure, but the region of attraction of its mass equilibrium. So that's exactly what we care about. How likely it is if when we start the dynamics at some point in the simplex that we will end up in the good equilibrium versus to the bad equilibrium or versus somewhere else. Now, there are a lot of assumptions that I make here, and I will discuss them. So for that purpose, we want to define the average price of anarchy. What do we change here? We again take the same numerator, so the best possible outcome of the game. But at the denominator, we take the expected value of the social welfare in all mass equilibria. Okay, now that's a statement that should raise questions. So the expected value with respect to what, right? So one thing that we need to add here, of course, is the game dynamic, because different game dynamics, I call them here F, we can have different Q-replicator in mind. So different game dynamics will have different behavior. So, and also different distribution over the starting point will have different behavior. But the second we resolve it by saying, let's pick a point uniformly random in this model, right? But that's debatable. Someone can say it's more likely to take a point at the center of the simplex or at the boundary, close to the boundary, or something like that. In our analysis, we have taken uniform distribution. But what we need to understand is that to define such a measure of performance, first of all, we need to make it dependent on the dynamics. Different dynamics will give here different performance, whereas here it's a static performance measure. We don't have the dynamics in price of anarchy. And the second is that to take this expectation here, we need that all trajectories of the dynamics go somewhere, right? Go to some equilibrium, because otherwise, if they do weird things, if they cycle, if they are chaotic, what does it even mean to take the expectation of the social welfare of X star, right? What is X star here? So it's the limit point of a trajectory, but if the trajectory doesn't have a limit point, then it doesn't make sense. So the first point to notice here is that when we define an average performance measure, we need many things. We need to have an initial distribution over points on the simplex. Maybe we can take the uniform without much debate. Then we have a dependence on the game dynamics that we choose, maybe different for every player or maybe the same for every player. So this depends on that. And the third and most important or most limiting, let's say, assumption when defining such a measure, average measure, is that it is well defined only if the game dynamics converge point-wise to mass equilibria for almost all, let's say, points. So that this expectation, let's say we can have, of course, a set of measures 0. Just give me a second. We can have a set of measures 0 where they don't converge. But yeah, if we have, let's say, chaotic behavior of or cycles, then this will create problems in the definition. Let's see now a little bit more, and if there are any questions, maybe we can discuss them here. Again. Let's go to the figure first, and let's see in the game that, and then we will discuss the results that I present here. So let's look at this figure. We have again courtesy to shift my cursor. So we have here the zero replicator dynamics, the gradient descent, and we see the region of attraction of the good equilibrium, the one that we want to reach down here. And now the region of attraction of this equilibrium is 78% of the whole simplex. If we take the standard replicator dynamics, it's only 73. And if we choose the Q equal 2, the log barrier dynamics is 68. So we see that different dynamics have different behavior. And of course, this affects the average price of anarchy, which is simply a weighted average, right? This area times 2 plus this area times 1, the bad equilibrium, because the trajectories that go to the mixed equilibrium are of 0 measure, so they do not matter. All right, so now this is a numerical result, and the question is, in this type of games, in stack hand games, 2x2 stack hand games, which let's say are in this parametric form that we had before, this gamma alpha beta, sorry that I'm going back, this one here, essentially they capture all symmetric 2x2 potential games, right? That's not very hard to see. Excluding the ones that are dominant solvable and which are not very interesting in terms of dynamics and the equilibrium selection problem. So, right. So what we observe here in this triplot is that all the regions of attraction, go through the mixed mass equilibrium. So the boundary of the regions of attraction, what we call the separatrix, which separates the regions of attraction from the equilibria, go here at this point through the mixed mass equilibrium. And essentially what determines the size of the region of attraction is whether this mass equilibrium here is above the diagonal or below the diagonal. Because it has to go through this equilibrium, regardless where it is. The comparison between the different dynamics will depend on whether this equilibrium is here or here. Right, maybe this is not very clear, but I will try to clarify it on the next slide. Let's first focus on the results of this slide. What they say is that the gradient descent dynamics, so 0RD, outperforms standard replicator. And this is an if and only if statement. That's what I mean here with the opposite also. And also we can offer here a bound of the average price of anarchy of gradient descent is upper bounded by 2. In the game, where the good equilibrium is also risk dominant. I haven't defined what risk dominant means, and maybe a good point is to let me do it here. Let's have a look at this figure, and maybe it will be clear. And I'm also towards the end of my slide. Right. So what we have here is that the regions of attraction are monotonically increasing in Q in symmetric 2x2 games. But the performance depends on the risk dominance, and there is no single best game dynamic. That's the result. So first, let's focus on this case. So we have our original very simple game coordination. Maybe this image is now a bit clear. It simply overlays all the boundaries of all regions of attraction. So here, simply the straight line corresponds to this straight line. This curve here for r equal 1 corresponds to this curve here. Here we have q equals 2. And as you go from blue to this darker color, we have the regions of attraction of the separating lines between the two regions of attraction for largest values of q. As you see, all of them have to go through the equilibrium, through the mixed mass equilibrium, right? So this is a point that has to be here. And for all of them, except for q equals 0, they have also to go through the two corners of the simplex. So I see some comments in the chat. Sorry, maybe there are questions. Okay, maybe I will discuss that later because they are very related. I will discuss that later because it's an interesting point. But let me first compare here, clarify the point of risk dominance. Now look here at the second game that I'm looking at. So pay attention to the payoff matrix of gamma. And now see here what we changed. The only thing that we changed is that now this, and I'm not sure even I did it in the correct way. I think the -5 has to be here, and here it has to be the other way. Sorry about that. Yeah. Yeah, think of -5, 0 and 0, -5. Now here, what does it mean? It means that the second equilibrium, the 2-2, which is the payoff dominant, which is the good outcome, is very risky, right? So if you play this strategy, but the other player doesn't do that, you get a -5. Think of the rewards reverse, sorry, -5,0. I think I can write here. Yeah, it's -5,0 and 0, -5. So if you play the strategy, you are player one and play the strategy, and the other player for some reason plays here, you get a -5. So it's very risky. And this is exactly what we find here affecting the dynamic, because it affects the mixed mass equilibrium. So the mixed mass equilibrium in this case is down here, and now everything is reversed. So now the worst dynamic with the worst region of attraction is the straight line, which is the gradient descent. Standard replicator is better, and as you increase the Q, it's even better. We don't have an exactly a game theoretic interpretation of why this is the case, which would be an interesting point. But essentially, what matters is what I want to say as a takeaway here is that the best equilibrium does not have always the largest region of attraction. It depends on risk, right? It depends on the mixed mass equilibrium, and the mixed mass equilibrium depends quite a lot on the riskiness of the good equilibrium. And even worse, if we even look at what happened here now, let's remove that. Now it's correct. And this monotonicity of the regions of attraction fails even in the simplest generalization of the previous game. Not generalization, variation, right? Here have an identical payoff game, not symmetric. The payoffs are identical. The game is 2 by 2. And here again, we plot the boundaries, and they are not monotonic. As you see here, we have this flap of the regions of attractions of the separating lines. They all go through the mixed mass equilibrium in this game, but here we don't have a result that the regions are monotonic. So here it's just this fancy, let's say, colored area. It's just all the separating lines overlaid. Maybe it's not very intuitive, but again, what this slide aims to say is that, let me recap here actually. What we know is that we can compare. The takeaway here is that even in a class of 2 by 2 games, this stacked hand family of games which captures all potential games in the 2 by 2 case that are not dominant solvable. Even there we don't have a unique recommendation. So in some cases, gradient descent is better than standard replicator. And in some other cases, replicator is better than gradient descent, let alone the other Q-Replicator. The dependence there, which one is better, can be explained through the riskiness of the good equilibrium. Not exactly which is better, but how risky it is. If we try to move a bit further and look, for example, at identical 2 by 2 games, identical payoff 2 by 2 games like this one here, we don't have the result anymore. So we don't have a result that something is better than the other. We don't have a monotony. That's it. Maybe the figures are a bit confusing here, but that's it. The whole takeaway here. Of course, many open questions here. The references that I have in this part, and that was it actually, are. This is because it's an ongoing research that we have been doing with Yanis and Yorgos. So they had an initial paper where they introduced this average case performance, and then we followed up with this analysis of this comparative analysis between gradient descent and Q-Replicator. Now, if there are again other papers, apologies that I don't cite them here. Right, yeah, but that was more or less what I want to show. Thanks a lot for your attention. Can go to the questions in the chat now.
Thank you.
Thanks a lot.
Thank you, Stefanos.
Great. Yeah, question time.
Thank you. Yeah, there is a priority for the questions in the chat. So let me, in the comments in the chat, let me read them. So the first one, hi, Bayet. Is there any way of generalizing to when you don't get point-wise convergence by considering the time average payoff of trajectories that don't converge to a limit point? Yes, sounds reasonable. And thanks, Yannick, for your response. I will read it here. Well, if they converge to a limit cycle, such as the time average payoff over the trajectory is well defined, then I guess so, I agree. But for the single population replicator dynamics in a batch rock, paper, scissors game, the time average itself does not converge to a point, but to the sub triangle, so the time average over a cycle is not well defined. Yeah. A very good point. And I don't know if you want to add something to that. Yeah.
So I would be more interested personally to hear what Ed has to say, because I haven't read his paper. So he say it can be done for the dynamics and replicator dynamics, and I don't know exactly what can be done and how and for which dynamics. So if he wants to tell us, I'm happy to listen.
I presume you mean Ed Hopkins, definitely.
Yeah.
I would also like to know.
Yeah. Let me also.
Yeah.
Yeah. Thank you, and sorry for the. Yeah.
No. I mean, sorry to it's all a long time ago and across many disciplines. So I mean, I don't think it directly relates. So as Yannick said, it's really about rock, paper, scissors, right? So where you have a mixed equilibrium, which is the attractor, or in this case, the repeller, right? And you can cycles around it rather than this, rather than the stag hunt game where you have a very different set of dynamics. So it may not. So Edward's question may not relate to this because you have in the stag hunt you definitely converge to a pure equilibrium anyway. But in a game where you have only an unstable equilibrium, then you can actually look at the time average of a cycle, because you can show that for best response dynamics that you converge to a limit cycle, and again that potentially this limit cycle therefore has a time average. And we actually invented a concept which is admittedly no one picked up on, called the time average of the Shapley polygon, precisely because of this TASP. And it does exist for something like for rock, paper, scissors. So you can think of it in that way as an alternative of convergence to a point. But it's only in some very special cases. I think that it's that you basically have to have a unique equilibrium which is unstable, which is quite unusual in the set of across all games. Anyway, that, as I said, is not necessarily related to, and therefore it doesn't cover stag hunt, for example.
Because of the structure of the equilibria, though, right? Yeah. And this is also looking at comparing performance of different dynamics.
No. So no, I just picked. It's really just about Edward's question, which is quite specific, and it touches on that. But it's a bit of a tangent to actually what you were talking about.
No, but it's actually it can help to generalize, right, to settings where you don't have this convergence, I think.
Yeah. Meanwhile, I see that Peyton Young seems to have a question in the chat, which is maybe more relevant.
So should I jump in and explain? So
yes.
There is, of course, a different approach, I'm sure you're aware of it, in which instead of going to the deterministic dynamic, you keep the stochastic term, which you did have for a while there, the exploration part, and then you can compute the ergodic distribution of the process. And so then you get a kind of a different approach in which is independent of the starting position, but of course will depend on the degree of stochasticity. But you would be able, using the ergodic distribution, to compute the expected welfare, for example. You can also look at things like the probability that the process is in a neighborhood of one or the other equilibria, the risk dominant or the payoff dominant. So all of that, there's a significant literature on this that uses the concept of stochastic stability. So if you're not familiar with that, that might be a different, set of literature that sort of complements what you're doing here.
All right. Yes, I'm not familiar with that.
Can I give a plug for my book?
Yes, please.
So you can find out all about this in the just published book called Spontaneous Order, Oxford University Press.
All right. Fantastic. Okay, that's great.
Thanks.
Thank you. Thanks a lot for the
Is there a
recommendation. Yeah,
discount for the participants of the?
Yeah, fantastic. These comments are exactly what one expects. That's all this for.
I had a question regarding, so you came to the replicators and Q-Replicators through experience-weighted attraction, and I was wondering how this behaves with respect to rescaling of payoffs. Like if you add a large constant to all payoffs, so I guess the effect is that the term in log of xi minus sum of xk log of xk will be then less important. Or if you multiply all payoffs by a constant, right? What I was wondering, like if you have negative payoffs rather than positive payoffs, so somehow when you don't play an action and then you discard it by y minus gamma, somehow it increases your score. Why if you have positive payoffs, then actually it will make this action less attractive because you haven't played it. And so I was so for the standard replicator dynamics, if you add a large constant, so making all payoffs positive, or if you subtract it, making all payoffs negative, it doesn't change anything. It seems that something is happening, which might be reasonable, right? But I was just wondering whether you had a sense of all the standard rescalings that have no effect on the replicator dynamics change experience-weighted attraction.
I disagree here, Yannick. We discussed it, last week. If you scale by a factor your payoffs in the replicator dynamics, independently of the other player, then it reacts stronger to the person. So the additive thing doesn't make anything. That's correct. But if you scale up, then the dynamics changes. And that's, I find, not scale invariant. And we were wondering about what this means.
So if you add a constant to all payoffs, it doesn't
multiplying. I'm multiplying with a positive.
So I agree with that. If you have a single population dynamics, it's not important.
Yes.
If you have a multi-player population dynamics, if you multiply the payoff of player 1 by 10 and not the payoff of the other players, then it's as if you were increasing the speed of adaptation by a factor 10 in the population 1 compared to population 2. That would be one way of understanding it, right? It's true that, okay, I usually work with a single population replicator dynamics, and so that might be why, I forgot that. But if you add a large constant, it doesn't change anything. Why here, for experience-weighted attraction, it seems important whether payoffs are positive or negative. But I see that Panayotis is raising his hand, so I don't know if this is for another question or for answering that. Yeah, we don't hear you, Panayotis.
Yes, I know. I was trying to unmute myself. No, it is for another question. I had another question, so I'll wait for you to finish if you want.
All right. Yeah, regarding the previous, I think, okay, adding the constant, right? It will cancel out, right? If we have Ri plus some constant, and then we have minus the summation xk rk, so it will be everywhere there, and it will disappear.
Yeah, but that's because you. No, but if that's because. I don't know. Maybe Maybe. I mean, I had the impression that somehow, I mean, whether the payoff were positive or negative would mean that would have some importance for experience weighted attraction, but you know, I might be wrong. Yeah, I see. Yeah, I understand what you said there. That's true. So yeah, I don't know. Okay, maybe it was a wrong.
About negative and positive, I haven't thought about it. So if these are negative,
No,
generally we don't.
Yeah, at least it doesn't change anything, right? So
because we can add the constant and make them positive.
Yeah,
and the dynamic will be that. Yeah, maybe that's. But now, if we multiply, now the effects of multiplication essentially, because we had a beta and gamma here in the beginning, so these are essentially what you multiply the rewards here, and here you multiply exactly, and then in the form that I'm used to see, everything goes into the t. So you just need one constant. You rescale everything here. You can even keep it in front of the reward, but the thing is exactly what you said. If you make the ln very large compared to the rewards, or the rewards very large compared to the ln, that's and all is captured by this t in the end. You can have it as 2 parameters, but I would say the effect is you can study the system. So Sato and Kratz will keep the 2 parameters in their analysis, but I think it's from what I have seen in the rest, it's the same to just keep one and do the analysis with that. Because it's the relative size of the two that matters, right? That's what I understand here.
Okay. Panayotis, if you want to.
Yeah.
Yeah. So my question was quite a bit different and had to do with the size of the Bayesians of attraction.
Yeah.
Now, if I'm not mistaken, you're measuring the volume with ordinary Euclidean volume on the simplex, right?
Yes.
Okay, but now, depending on how you see things, and I'm basing this on the derivation that you showed us, the initial condition of the dynamics is not necessarily a mixed strategy on the simplex, but an initial propensity score profile, in the space, like where you showed in the in the space of payoffs, or rather of aggregate of scores, or however you want to call it. Yeah, let's say in the space of payoffs. Now, there, my question is, if you take a uniform distribution of, or rather, if you measure things and volumes in the space of payoffs with Euclidean distance, which is where you have your initial conditions living, in a sense, and where you would like to measure your Bayesians of attraction. Would this change? Would this affect the result? Because definitely this incurs a nonlinear change of volume form on the simplex. And of course, I realize that the space of payoffs is unbounded. But let's say that you consider that you take your initializations in a huge cube of the dimension -m to the -m, m to the whatever strategy space you have. So. Yeah, this is just an open-ended question. If you have any comments or input or whatever.
Yeah, that's a good question, and that's a very good point actually. And I think yeah, let me see. So as you say, all right. So I think that some trajectories that converge here, for example, yeah, it was not clear exactly when we looked at the problem how to measure volumes in the payoff phase. For example,
why not uniformly?
But in the -m, but you have this increasing payoff. So let's say some trajectories go to here and take 2 ever after. So the rewards for these trajectories keep increasing.
So, I mean, you would still be measuring volume and comparing volumes of initial conditions, right? So you would be comparing volumes of different initialization regions. or
correct.
you could examine, for instance, whether as the payoff bound goes to infinity, whether the ordering of the basis of attractions is respected, or the true question, my true question is there, or do you believe there is any case of your observation being metric dependent, meaning what you observe as being the largest basin of attraction being an artifact of the metric that you're using to measure volume? That's my true question.
Yes, I understand it. I mean, I want to say no, that it's not an artifact. It seems to me that it holds, but actually that's hard to say without having proof, because I know that many weird things can happen in if you look at the payoff phase. So I would say that's a good point, and maybe it's something definitely to look at. And a very good hint, and maybe that can provide even more insight here, and to prevent the problems that we have when measuring distances in the simplex. Yeah,
okay.
That's a good point.
Yep.
Definitely.
Yeah, sure. I was just wondering if you had looked at it. I don't know. Can I be allowed a quick follow-up?
Yes, please.
Of course.
Okay, thank you. Do you think, I mean, if we go to n-player coordination games, and again, we stick with the same kind of binary structure for the action set. So let's say 2x2x2x2 games with the same, coordination type, equilibria, risk dominance, etc., all that good jazz. Have you got any idea which of your results may extend, and in which way, etc.?
I mean, that's one problem here. We only have some understanding which results extend in two-player games with more actions, with numerical simulations. But in some numerical, which confirm that the results continue to hold. Let's say when we go to increase the number of actions and have, let's say, diagonal games, for example, where you have many equilibria. The experiment that we did in, I think it was exactly as you said, 2x2, 3 players, two actions each. I think there we got lost because I mean, you can only get numerical results. You have more, even it's not well defined what. How to define what's the risk dominant here, which is it can be very different risk profile for different players. So you need to look at special cases where, let's say, you have the common equilibrium being less risky for everyone. And the actual problem is that, okay, you can run simulations, you can get more initial, let's say, for some games, but how do you get here now to calculate analytically, as we did here, the regions of attraction? I mean, maybe it's mathematically possible, but it seems very difficult at least. Yeah, I don't know. I don't know what you think about that.
My dirty, quick and dirty solution to that would be numerically, to calculate it numerically.
Yeah.
But yeah. But yeah, no. Of course, I understand the difficulty. I was just wondering if you had any insight. So yeah, thanks a lot.
Thank you. Yeah, only two insights, essentially only two players and action games. Yeah, there we have insights that they continue to extend.
Perfect.
So
Thank you.
regions of attraction. You're welcome. Yeah, very good question. Thank you for the question, and for saying that way. Yeah, maybe that comment here is that I mean, the regions of attraction look very interesting here and very meaningful, but I really, we didn't have an idea. I don't have an as a group. We didn't have an idea how the theory can extend to larger dimensions, right? How you can calculate what, except of sampling too many points and saying, okay, now I sample too many points, I have an estimate of the region of attraction of that particular game. So that's a big open question. But on the other hand, I don't know of any tools to approach it analytically. So it's maybe it's a difficult one. But thanks a lot for this and for the comment to look on the payoff.
Further questions? Okay, so I stopped the recording.